Dear students, in this short video we will talk about how to assign oxidation numbers to atoms in different compounds. Alkali metals, say the first A group of the periodic table, which has like lithium, sodium, potassium, etc. The oxidation number in their atomic state when they are in the form of atoms, then it will be 0, and when they are in the form of their ions or they are in their compounds, in all of their compounds, their oxidation number is +1. Say for example, we have sodium chloride, or say potassium sulfate, or say we have lithium nitrate, or you can quote any salt of these elements. The oxidation number of sodium, potassium and lithium in all these compounds will be +1. So we can say that the oxidation number of alkali metals is fixed, that is +1 in their compounds, but when they are in their atomic form it is 0. Similarly, if we have alkaline earth metals, and alkaline earth metals have certain elements, like we have magnesium, calcium, barium, etc., and they belongs to the second group of periodic table. When they are in their atomic state, their oxidation number is 0, but if they are in their compounds, like say we have calcium chloride, or we have say barium sulfate, etc., their oxidation number will be +2 in all of their compounds. Means in alkali metals it is +1, and in alkaline earth metals you need to remember these elements. Most abundant of these are calcium and magnesium, and in their compounds they have an oxidation number of +2. And this is owing to the fact that alkaline earth metals have 2 electrons in their outermost shell, which can be removed to make +2 ions, hence their oxidation number is +2. Other frequent elements which are there, like we have hydrogen. Hydrogen have different forms. For example, hydrogen may be present in atomic state. Hydrogen may be present in its diatomic molecule. In other compounds of the periodic table, other compounds like hydrochloric acid, like water, or with metals. Say for example, sodium hydride, calcium hydride, etc. So these are different forms. Hydrogen in its atomic form or its molecular form will have an oxidation number of 0. In its compounds, its oxidation number is +1, but when that hydrogen is attached with metals, in the form of hydrides, the oxidation number is -1. That -1 is owing to the fact that the alkali metal, again oxygen may be present in the form of oxygen atom, in the form of its homonuclear molecules like oxygen and ozone. It may be present with frequent elements of the periodic table to form compounds like, say, water, like for example oxides, and oxygen may also be present in peroxides and superoxides. For example, we have sodium peroxide and we have potassium superoxide, and oxygen may also be present along with fluorine. And these are the certain forms of oxygen which needs to be considered when assigning oxidation number. Oxygen in its atomic or molecular forms, like these three, the oxidation number of oxygen in these compounds will be 0. In oxides, normal oxides, oxygen is highly electronegative, other elements are electropositive, so here we have to say that oxygen has -2 oxidation state, because we have already discussed that the hydrogen will have +1 and alkali metal will always have a +1. So if it is 2 into +1, that is +2, the oxygen ultimately will have -2 because overall charge on this compound is 0. So the oxidation number of oxygen in these compounds, similarly in water, it is -2. And most of its compound is -2, except when oxygen is bonded with fluorine, because fluorine is the element with highest electronegativity, even higher than oxygen. So in this case, fluorine will have a negative oxidation state and oxygen will accord. On the other side, when we have peroxides, alkali metals, as we have already discussed, they will always have a +1 oxidation number, and then the oxidation number of the oxygen will need to be calculated accordingly. Overall charge is 0 because there are 2 atoms, so we can say it is -1. In superoxides like potassium superoxide, alkali metal potassium is here, its oxidation state is +1, so again we have to calculate. The halogens are concerned in the form of atoms, in the form of their diatomic molecules, will have a 0 oxidation state, while in their binary compounds with elements which are electropositive than halogens, binary compounds are compounds made up of 2 elements, halogen will have -1 oxidation state. Other than that, because halogens belongs to 7 group of the periodic table and contains fluorine, chlorine, bromine and iodine, which are more frequent as 13 is there. Fluorine will always have a -1 oxidation number in all of its compounds. atom and fluorine molecule, where the oxidation number will be 0, as we have discussed here. Other three halogens, chlorine, bromine and iodine, have variable oxidation number depending upon the type of compound which is there, and we can elaborate that with the help of certain examples. Say we have a compound HClO or hypochlorous acid, or HClO2, that is chlorous acid, or HClO3 and HClO4, that is chloric acid and perchloric acid. In these compounds, we have three elements. So halogens will have a variable oxidation number here. Hydrogen will have +1. Oxygen will have -2 as in its compounds, and chlorine will have a +1 oxidation state because overall charge is 0. Similarly, if we calculate here, it will be +3. If we calculate here, it will be +5. If we calculate here, it will be +7, because 4 oxygen atoms. So 4 into -2 and +1 and +7. So if we calculate all these, it will be overall 0, and the oxidation number of halogen is 7. So we can say that these halogens have variable oxidation number, which is +7, +5, +3 and +1 in their compounds. This is owing to the fact that the halogens have 7 electrons in the valence shell, and these can be used for. So this is overall concept of assigning oxidation numbers to the elements which are most frequently occurring in compounds: alkali metals, alkaline earth metals, hydrogen, oxygen and halogens. If we speak about other compounds, if we speak about elements of other groups, like say we talk about the fourth group of the periodic table, that is carbon, silicon, germanium, tin and lead. It's fourth group, and the electronic configuration is ns2, np2, total 4 electrons. 2 of them are in the s and 2 of them in the valence p subshell. So this group will have 2 possible oxidation states. One is 2, the other is 4. 2 owing to the bonding when only p electrons are involved, and 4 when all the s and p electrons are involved. Say for example, we have lead chloride in its +2 oxidation state, and we have lead chloride in its +4 oxidation state. Here binary compound halogen will have a -2 charge, lead will have +2 in this very compound, and lead will have +4 in this very compound. So 2 variable oxidation states. So it depends upon electronic configuration. Similarly, if we talk about any other group of the periodic table, say for example, if we talk about fifth group, we have nitrogen, phosphorus, arsenic, antimony, bismuth, and phosphorus. Again, the fifth group has 2 electrons in the S and 3 electrons in the P. So variable oxidation states will be 3 when these 3 p electrons are utilized. For example, we have NH3, we have PCl3, we have P2O3. If you calculate the oxidation number of nitrogen and phosphorus in these compounds, it will be 3. The other possible oxidation number of these compounds owing to their valence shell electrons is 5 when all the electrons are involved. Chemical bonding. For example, you have PCl5, you have P2O5, or you have H3PO4, or you have N2O5, or you have HNO3. In all these compounds, these central atoms belonging to the fifth group, that is phosphorus and nitrogen, they have an oxidation number of 5. So we can say it depends on valence electrons, and it also depends upon how many valence electrons have been utilized. Again, if we want to discuss, say, the sixth group of periodic table, the oxygen family, we have oxygen, sulfur, selenium, tellurium, polonium, etc. And most frequently used elements of oxygen and sulfur, they have 6. So they are 2 short of their octet. The possible oxidation state could be 2, which will be -2 in most of the cases. For example, H2S and H2O. -2 oxidation state of oxygen and sulfur, based upon the fact that hydrogen will have +1 oxidation state. And similarly, they may have 4 oxidation state owing to the fact that they have 4 p electrons. Electronic configuration is NS2 and NP4. So other possibility is 4. For example, sulfur dioxide. Okay. For example, sulfurous acid, H2SO3. But that is only possible in case of sulfur, because in case of oxygen only second shell is involved, which does not have a D availability of the D subshell. So sulfur will have 4 oxidation states. Similarly, if all the electrons in the valence shell have been utilized for chemical bonding, we can have compounds like sulfuric acid, sulfur trioxide, or all the sulfates. So this oxidation state in these compounds for sulfur, if we calculate, it will be 6, positive 6, where all the 6 electrons have been utilized. So we can say oxidation number depends upon the group number as well, and the number of valence electrons, and the number of valence electrons being utilized in that very compound. So this was all about how we can assign oxidation number to certain elements. If we calculate, for example, with a example, let's say we have this compound potassium dichromate, and we have chromium, and chromium belongs to D block elements, and we have not yet discussed any D block element to assign their oxidation number. So we can make use of the rules we have discussed about the alkali metals and oxygen to calculate the oxidation number of chromium. Alkali metal have positive 1, so we have 2 atoms of potassium, that will be 2 into plus 1, plus we have 2 atoms of chromium and we do not know, so we will write X unknown, and we have 7 atoms of oxygen, and oxygen has a -2 oxidation number in its compounds. And the sum of these must be 0 because there is no charge on potassium dichromate. So we have to find the value of X. And if we calculate that, it will be 2 plus 2x plus minus 14, which will comes out to be that the X is equal to 6, positive 6, which will be the oxidation number of chromium. So this is how we calculate all these.